Alright, welcome back. So our robot is now visible in simulation, but it cannot move yet. In this module, we will introduce ROS2 control. ROS2 control is the standard framework used to control robot hardware. It works the same way for simulation and real robots. This is very important. It means your control system does not depend on the robot itself. You can replace the simulator with a real robot later, without changing your logic. ROS2 control separates three things: hardware, controllers, and communication. This separation is what makes ROS2 scalable and professional. So, at the center we have the control manager. This is responsible for loading and running controllers. Controllers are nodes that compute commands, for example, position controllers, velocity controllers, and trajectory controllers. Then we have the hardware interface. This layer connects ROS2 to a real robot, a simulator like Gazebo, or a mock system. Finally, we have broadcasters. They do not control anything, they only publish robot state like joint positioner. This architecture is powerful. You can replace any sensor, any actuator, any control logic without breaking the system. First, we install the ROS2 control package. This package provides the control manager, standard controllers, and integration with Gazebo. We do not source ROS2 here, because it was already done earlier. Now we connect our robot to ROS2 control. We create a new Xacro file. This file defines the hardware interface for our robot. Each join defines a command interface and state interfaces. The command interface tells ROS2 what we control. Here we use position control. The state interfaces provides feedbacks like position, velocity, and effort. At the bottom, we add the Gazebo plugin. This plugin connects the simulator to ROS2 control. Finally, we include this file in the main robot Xacro. Now the robot is ready to be controlled. Now we define our controllers. The control manager will load them automatically. First, we create a joint state broadcaster. It publishes the joint states topic. This is required for visualization and feedback. Then we create a joint trajectory controller. This controller receives motion trajectories. It allows smooth and timed movements. We define the joints, the command interface, and the state interface. This configuration defines how the robot will move. Now we update the launch file. We add controller spawners. These are the nodes that load controllers at the runtime. We must ensure correct order. The robot must be spawned first, then the joint state broadcaster, then the ARM controller. We use event handlers to enforce this sequence. This avoids startup errors. Now we will build a workspace. We only rebuild the description package. Then we source the workspace overlay. Now we can launch the simulation. Watch the terminal carefully. You should see controllers being loaded. So after launching our Gazebo file, we have found an error. So a plugin is not found because it has another name. So we fix that and we can relaunch and resource our project. We will verify that everything is running correctly. First, we list controllers. Both controllers should be active. Then we check joint states topic. This confirms that the robot is publishing its state. This feedback loop is essential. It allows closed loop control. Now we send a command to the robot. The controller exposes an action interface. This allows asynchronous execution of trajectories. We define joint names, target position, and timing. This is not just a command. It's a planned motion over time. Watch the robot move smoothly. Now we create a Python node. This node acts as an action client. It sends trajectory programmatically. We define multiple positions. Each position has a timestamp. This is how real robots operate. They follow trajectories, not single commands. You can now implement pick and place, repetitive tasks, or custom motion logic. ROS2 control provides management tools. You can list controllers, inspect hardware interfaces, activate or deactivate controllers. This is useful for debugging and runtime control. So in this module, you'll learn how ROS2 control structures robot control, how to connect a robot to controllers, how to send trajectories. You now have a full control pipeline, from sensors to processing to controllers, finally to actuators. And this pipeline works for both simulation and real robots. In the next module, we will add a camera. This will introduce perception into the system.